We're going to do some nuclear today. We're going to talk about nuclear fission first, okay? And we'll do fusion and a couple other things. And I'll work out some problems for you. Nuclear fission. Okay, the word fission for nuclear comes from biology, actually. And it's the splitting, like a cell splits. It's the splitting of an atom, splitting of atom. Well, really, it's the splitting of the nucleus, okay? Okay. Now, the fuel, not everything fissions, not every nucleus fissions. So the fuel that's going to be used is going to be uranium, okay? Uranium. And uranium is just a rock that you find in the ground. So here's a piece of uranium. Okay? It's just a rock that you dig out of the ground. Now, there's two isotopes of uranium. One is the 235 uranium with 92 protons. That's what makes it uranium. And there's an isotope 238, which has 3 more neutrons than the 235. Okay, this is so when you dig up a piece of uranium from the ground, you have U-235 and U-238. However, the U-235 is less than 1%. So it's 0.7% of the rock is that. And 99.3% is the uranium-238. Okay. Now it turns out, of course, uranium is a limited resource, right? It's limited. It's a limited resource. We don't have that, right? Infinite amount, because it's just something you dig out of the ground. It's a limited resource. And it turns out that this is not the isotope that we use. It's going to be this stuff, the 235, that is fissionable. So this is the stuff we're going to use to fission. Okay. Notice we can only use less than 1% of the uranium that we found in the ground. So it's very limited, right? Very, very limited resource. So it will run out. Okay, very, very limited resource. So let's talk about the fission and tell you what happens now. We're going to take a neutron. Okay. We're going to take a neutron and a little circle. This will be my little thing. A little circle is going to be a neutron. And a big circle is going to be the uranium-235. Okay? And what we want to do is we want to take a slow neutron. Now, I say slow. If it's moving too fast, if a neutron moves too fast and we shoot it at this guy, then it just passes through very quickly without causing any trouble. But we're going to shoot a neutron at the uranium, and when it hangs out, because it moves slow inside, it's going to cause the nucleus to fission. So let's do our picture, a simple picture. Okay, so here's my little circle. That's the neutron. Now it's going to hit this very big, much bigger than I'm drawing. Remember, it's got 230. So there's my uranium. Okay, now the uranium splits. Okay, I'm going to say uranium splits into two lighter elements. Uranium splits or fissions into two lighter elements. Okay. So it's going to split up like this, and it's going to make two other elements, okay? And I'll do this like this. Okay, they're not so big, okay? One of them is barium, and the other is krypton. These are two lighter elements. Okay. And these elements are called fission products because they're the products of fission. Fission products. Okay. So if I ask you on an exam, which of the following is a fission product, it would be either or both barium and krypton. Okay. But what I really care about is that out of this reaction comes two more neutrons. Okay. Neutron and a neutron comes out. Okay. These are neutrons. Sorry, my ends aren't so good today. Okay, two neutrons. So this is the reaction of fission. And of course, every time a nucleus fissions, right, what comes out is there's going to be energy released. Okay. So I'm going to redraw this picture and I'm going to let's ignore the fission products for now. We're going to ignore fission products, ignore the fission products. I'll talk about those later, but they're going to get in the way, and I don't want them to get in the way right now. Okay, so we're going to ignore them. And I'm going to redraw this picture that I just drew in purple. We're going to redraw it, but without the fission products, okay? Well, we're going to have a neutron coming in. That's the little thing. It's going to come in and hit this uranium, right? I'll put the 235 here for the first one, okay? There's uranium. And there's my neutron. Now, what happens is we're just focusing on the neutrons that come out. So what's going to come out of here? Remember, we're ignoring the fission products. There's a neutron. And there's a neutron. And if you have things just right, then each of these neutrons can themselves hit a uranium. See, remember the big circles of uraniums. And once again, a neutron comes out and a neutron comes out. And the same for this one. A neutron is emitted and a neutron is emitted. Well, again, each of those neutrons now can hit another uranium. Okay. Okay. And you get the picture now. Now, two more neutrons come out. Two more neutrons come out. Each of these two neutrons on average comes out. Wow, look at this beautiful picture, right? And you could do this yourself. And then, of course, if they hit uraniums, and I'm not going to keep going with this because I'll go forever. Excuse me. And again, I'll just draw the arrows. Neutrons come out, neutrons come out, neutrons come out. Remember, every time energy is given off, every time the nucleus fissions, and there's fission products, right? The barium and krypton. Neutron, 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 neutron. Okay? Getting tired here. Okay, good. So we started with one neutron. We went to two neutrons. We went to four neutrons. We went to 8 neutrons. Now we go to 16 neutrons. It's growing what we call exponentially, exponential growth, exponential growth. Okay, it keeps growing. And this is what we want this to happen. We want this to happen in a bomb. So this is what takes place in an atomic bomb. Atomic bomb. So here, what we have is an uncontrolled chain reaction. Uncontrolled, because it keeps growing, controlled chain reaction. Keeps growing and growing and growing and growing. Okay, well, I'm going to redraw this picture. Again, we're going to ignore the fission products. Okay, and I'm going to redraw it this way. Okay, I'm going to draw. There's my neutron coming in. There's my uranium-235. Okay. There's one neutron coming out, another neutron coming out, and there's another uranium. Oops, a little big, but that's okay. There's a neutron coming out. There's a neutron coming out. Okay. Draw another uranium. There we go. Neutron coming out. Neutron coming out. I'll do one more. Okay, two neutrons. Remember, I'm ignoring those fission products, fission fragments, the barium and krypton. Okay, it keeps coming out. Okay, now what we do now for this is we put up something here. Okay, I'll just stop it there. This is called a control rod. And the purpose of the control rod is to absorbs neutrons. Okay? And the control rods are usually made of heavy metals, cadmium, like you find in batteries, cadmium, and boron. So again, the test question, control rods are made of cadmium, boron, and they absorb neutrons. And the consequence of this is now we have a neutron comes in, causes this guy to split. This neutron causes another one to split. This neutron comes in, causes another to split. And what we have is a linear, not uncontrolled, but controlled chain reaction. Okay. And this is what we want. We want this to occur, want this to occur, want this controlled reaction to occur in a nuclear reactor. We don't want a nuclear reactor to be an atomic bomb. Okay, we want it to be controlled. Okay, so I want to talk about bombs and a couple of things in a second. Okay, so we have the uncontrolled reaction, right? Again, ignoring fission products. Uncontrolled keeps growing exponentially, and now we have a controlled linear reaction. Okay, so let me just remind you again. Remember, this is U-235. Okay, now U-235, if you remember what I said above, it's only 0.7%. Okay, that's a very, very small percentage. Now, if we want a chain reaction to occur, for a chain reaction, either linear or uncontrolled, like in a bomb, for a chain reaction to occur, the neutrons need to, I'll put find the uraniums, to find the 235 uraniums. Nuclei. That's 92, sorry, 92. Okay, let me erase that, I'm sorry. I'll make it a little clearer. So they have to find them. What do I mean by find them? Well, let's just see. That's less than 1%, right? Less than 1%, So if we have a system, and these are all uraniums, watch this, these are all uranium atoms, but 99, oopsie, sorry. 99.3% of these guys are uranium-238s. Now I'll put a couple of red dots here for less than 1%. Okay, so I'm going to put a red dot there, a red dot there, red dot there. Okay. Okay. Now these red dots say are the 235 uraniums. Okay. So suppose a neutron comes in and it finds this uranium and splits it. Now neutrons come off, but they can't find any more uraniums because there's not enough around. So there's no reaction. Nothing happens. That's why when you have a piece of uranium in the ground, there's no reaction. The neutrons that come off naturally cannot find anybody to split. So what we do with this fuel, with this uranium fuel, is or the engineers, they enrich the fuel. You don't have to know about all these numbers, okay? But I'm just telling you. They enrich the fuel to about 5% to 35 uranium rather than what it found naturally, rather than naturally occurring 0.7%. So they do this, enrich it to 5%, so that neutrons can find uraniums. So this increases the chance, increases the probability, we'll say, probability of a neutron finding a uranium-235. Okay, why am I telling you this? Why is this important? Finding a 235 uranium. Okay. Okay, so I'm going to tell you why. So now the uranium-235 is enriched to 5%. Okay. Well, physics, that's the important thing here. Physics, the laws of physics tell us that for a bomb, to make a bomb, where you have an uncontrolled, right, chain reaction, uncontrolled chain reaction, you need a minimum of 30 30%. Oh gosh, my handwriting. Okay, of 30% 235 uranium. And so we know from physics, we know that reactors cannot explode like bombs. Ha, isn't that, well, that's good. Reactors cannot explode like bombs. Remember this, because I'm going to tell you something in a little bit. Okay, is kind of scary. Okay, so reactors cannot explode like bombs. There's just not enough uranium-235. Now, I do want to say this, and I said this in for some of the classes, and this is what I wrote. I wrote something like this: neutrons everywhere. So I'll talk about this quickly and why this is bad. Neutrons are bad. Okay, so first let's talk about two isotopes of carbon. And I was surprised many students did not know what I was about to say. Isotopes of carbon. Okay, so found naturally is the stable isotope that our body is filled with. And we also have the other is carbon-12 with 6 protons. So this has 6 protons and 6 neutrons. The unstable carbon has 6 protons. That's what makes it carbon, but 2 extra nucleons. Okay. And what this carbon does then is, we're going to do more of these problems. It negative beta decays. Remember, negative beta decay, you add a proton. So if we add up the top, whatever's on top has to be 14 because 0 plus 14 is 14. And on the bottom, it's got to be 7 because 7 minus 1 is 6. And so this is now nitrogen. And so this is used in what's called carbon dating. In other words, when you have something, an organic material, bones, organic material, right? The organic material has naturally carbon 12 and carbon 14, but eventually there's going to be a certain percentage of carbon 14. If they know the half-life of this, which they do, I don't know it offhand, but they know the half-life of carbon 14. If they look at the percentage of how much nitrogen was produced, they can figure out how old the fossil is or whatever it is they're looking at. And that's called carbon dating, okay? And that's because carbon 14 is unstable. So this is an unstable isotope. What's the difference? It has 2 more neutrons. Now, in our bodies, we have things like oxygen. Okay? Now, oxygen has 8 protons and 8 neutrons. That's stable. But you can have unstable oxygen with oxygen 17 or oxygen 18, okay, etc. Okay? You can get anyway, what's the difference between oxygen 16, oxygen 17, oxygen 18 is the number of neutrons. So when you add neutrons to things, you can make, so neutrons, I'm going to write this, neutrons can make stable isotopes or can make stable isotopes become unstable. So if oxygen 16 gets hit with a couple of neutrons, it can become oxygen 17, oxygen 18, and etc. If carbon 12 absorbs some neutrons, it could become carbon 14 and become radioactive, right? We said radioactivity was an unstable nucleus, okay? Unstable. So up here, I wrote neutrons, neutrons everywhere. And this is, if we talk about a reactor, so inside a reactor, lots and lots of neutrons. Now remember what a nuclear reactor is. How could you remember? You don't even know. Well, a nuclear reactor, right? You fission, you split the 235 uranium, and of course you get out energy. And a lot of that energy is heat. And so this heat is used to boil water, to make steam. And remember how we made electricity? And this then, the steam moves the coils and magnets, moves coils and magnets or magnets to make electricity, to make electricity. Okay, so a nuclear reactor is just a teapot. Shh, don't tell anybody. It's just a big teapot. Okay, but remember the neutrons are everywhere. Neutrons, neutrons. So what these neutrons are doing is they're getting absorbed. They're getting absorbed by everything, absorbed by everything, absorbed. by everything. What do I mean, everything? I mean, it's being absorbed by the air. Remember, air is O2 and N2 mostly, right? It's being absorbed by water because you need the water to heat up and make steam. Again, we know that's H2O, doesn't matter. It's being absorbed by the control rods, right? That's the cadmium and boron. It's being absorbed, the neutrons are being absorbed by the fission products. Right? Remember the fission products are krypton and barium. And they're being absorbed by the reactors metallic core made of zircaloy, metallic core. It's called zircaloy. It's an alloy. Again, I won't ask that, zircaloy. And the net consequence is that all this stuff becomes radioactive. All this stuff becomes radioactive. All this stuff becomes radioactive because they become unstable isotopes, radioactive. Right? Neutrons everywhere, very, very bad. Everything's becoming radioactive. And then the question is, what do you do with this core when, and all this stuff is you have to find a place to bury it out west, somewhere in Nevada, miles underground, so it doesn't go near people for a very, very long time. So it's all very deadly, okay? But remember, reactors cannot blow up like a bomb, cannot blow up like a bomb. Okay, so now the other thing now that I'm going to emphasize is recall that this 235 uranium is only, right before they enrich it, but it's only 0.7%, right, naturally. So it's very finite. Okay, finite. So can we use the 238 uranium? The answer is no, because it does not fission. But they can make it into a fuel that it can fission. Now remember, this uranium is 99.3%. So there's lots of this stuff. There's lots more of this stuff. Right? So what they're going to do, this is very clever, and the details aren't important, but what happens is they take a U-238. I think you can follow what I'm going to do. Right? And they're going to add a neutron. Okay, a neutron has no charge, one up here. This is 92. And what it ends up with, 1 plus that is 239 uranium. See, 1 plus 38 is 239. 0 plus 92 is 92. So it's still uranium. But now uranium-239 is unstable. And this thing now, negative beta decays. Okay, so what you get up here is 239 again. 239 has to be there. And then you have something -1 has to be 92. So this has to be 93. And I believe that this is neptunium. Okay, that still is no good, doesn't it? But neptunium is unstable. And now this undergoes negative beta decay. Okay, so now we have element 94, and again, 239. So what has 94 protons? If we look in the periodic table, this is plutonium. Plutonium. Super deadly stuff. All of the plutonium on the Earth is human-made, okay? And so we call this stuff, this is plutonium-239. All right, Pu, plutonium-239. And this stuff, yes, can be fissioned. Yes, can be fissioned. So we'd have the same picture for this. A neutron comes in, hits the 239 plutonium. Forget it breaks up into other elements, but we don't care. Okay, I don't care about the fission products, but all I care about is neutrons come off. Same picture. Another plutonium hits another plutonium, right? Hits another, oopsie, hits another plutonium. Neutrons come off, etc. So exactly our picture for the uranium-235, we now have this picture for plutonium. So we just bred plutonium. So we made a fissionable fuel. Okay, we made a fissionable fuel. And that fissionable fuel was the 239 uranium. Uh, Plutonium. I'm sorry. Plutonium. And we said that was whatever, 94. Okay. And when we say we made a fissionable, we say we bred it, like you breed children, we bred it. And so when you making plutonium, this is made in what's called a breeder reactor. So if I ask you, what is the fuel that's created in a breeder reactor? The answer is plutonium-239. Okay. Now, breeder reactors, if we use breeder reactors and use the plutonium, these, remember the 239 plutonium came from the 238 uranium. But remember, this was 99.3%. So that means that the percentage now of 239 plutonium, remember, that's fissionable, is greater than, that's the greater than sign, 30%. Remember, 30% was the minimum percentage for a bomb. That was from physics. And so this means, and I'll write this in big letters, okay? This means that breeder reactors, which if we're going to go with nuclear in this world or in this country, then we're going to have to use breeder reactors. That's the military uses it to make bombs. This means that breeder reactors can explode like a bomb. Why would we use breeder reactors? Because we want to use that uranium-238, which is 99.3% of the uranium found in the ground. So we want it to last longer. So this means that breeder reactors can explode like a bomb. Scares me like a bomb. Okay. All right. And again, with all the nuclear waste, all these things from the neutrons, everything becoming radioactive, neutrons everywhere, we have to get rid of that waste, which is an environmental problem also. Okay, although there's no greenhouse gases because we're not burning fossil fuels. People want to go to nuclear. But if we go to nuclear, we're going to have to use these breeder reactors because we have to use the 238 because there's so much more of that. Okay. Now, in class, for most of you, I told you about stars and we are stardust, right? And so we talked very briefly about nuclear fusion, right? Fusion, for example, is where you take deuterium. Remember the isotope of hydrogen, one proton, one neutron. And if we smash it together at a high enough temperature, then we can get four helium 4, 2. And if we combine a couple of helium 4s, just add the tops, add the bottoms, smash these together. 4, 4, 4, you get 12, 2, 2, 2, you get 6, there's carbon 12, etc. And this is taking place in the sun and in all the stars. And we said this is nuclear fusion. And what we're doing is we're making the elements. So we call this nucleo for nucleus, nucleosynthesis to making. So we're making elements in the periodic table. Okay, so you combine carbon. So that's how we get lithium, potassium, oxygen, nitrogen, sodium, and all the rest of the things. And then that cloud collapses, makes the earth, and we are stardust. Hopefully everybody kind of remembers that. Okay. Um, what was I going to say about this? Oh, all right. So now I'm going to tell you one other thing, and then I'll do some problems. Okay. In Pay attention to this. In all nuclear reactions. Okay, and I'm going to summarize. Okay, all nuclear reactions, that includes radioactivity with alpha decay. So we have negative beta decay, positive beta decay, alpha decay. Remember, alpha is a helium 4 nucleus. Alpha decay, gamma decay. Remember, gamma is a photon, no mass, no charge, 0, 0 decay. uh, Comma, nuclear fission, and fusion. In all these reactions, okay, in all these reactions, mass, and I should take away the parenthesis. I'm going to just do this. Mass is, now I'll put a parenthesis, lost, because it's not really lost. Okay. In other words, this means that the mass in any reaction, alpha decay, beta decay, gamma, nuclear fission, mass you start with is not equal to the mass you finish with, but it's greater than the mass you finish with. Remember, in all nuclear reactions, right, in all nuclear reactions, don't forget, energy is given off. In all nuclear reactions, energy is given off. In all nuclear reactions, energy is given off. Energy is released. But Einstein, Einstein And he said this in 1905, 40 years before the atomic bomb was dropped, the two bombs were dropped on Japan. He said this in 1905, said energy is equal to m mass times the speed of light squared. In other words, energy and mass are equivalent. They're essentially equivalent. So what's happening is mass that you start with is greater than the mass you finish with, but then we have to add in the energy. But this energy is the missing mass. I'll put delta M, the mass that's missing that got converted times c squared. Okay, so this bit of mass that's missing was converted to energy. So the missing mass was converted to energy. Missing mass. In all nuclear reactions, there's mass missing, but it's not really missing. The missing mass is converted to energy. Okay? And that's what Einstein said. So you should know this. This is energy, this is mass, and this is the speed of light squared. So if this was 1 kilogram, and we know the speed of light is 3 times 10 to the 8th, c squared is about 10 to the 16th. 10 to the 8th times 10 to the 8th is 10 to the 16th. That would give 1 kilogram, could make 10 to the 16th joules of energy. And so the bombs that were dropped on Japan were about 2 kilograms, about 5 pounds or so. So only a couple of kilograms. And that much mass was converted to energy, and that much energy killed a lot of people. Okay? So energy and mass are equivalent. All nuclear reactions lose mass. And boy, that creates that missing mass creates a lot of energy because it's equal to delta M, that missing mass, times c squared. And c squared is 10 to the 16th over, right? 10 to the 8th times 10 to the 8th. So you get a lot of energy out for a little bit of mass. So nuclear gives a lot of energy. Okay. What I'd like to do now is I'll go through some problems that will some of the math problems. Okay. So let's see. Let's do this. All right. All right, so let's go through some of these half-life problems. Okay. The half-life of element X is 12 hours. Oops, oops, oops. I don't know. Where's the pen? Um, okay, so let's see. Cancel. I don't know what's going on. All right. All right. The half-life of element X is 12 hours. Oops, I don't want to do that. I don't know what's going on. Draw. Okay. Okay, so now we're back to drawing. Okay, so now we're good. All right. So forgive that red mark. Um, so the half-life is every 12 hours. So every 12 hours, the sample decays in half, right? So after 3 days is what? How many hours? I don't know. How many hours in a day? Right? There's 24, 24. So this is 72 hours. Right? That's 3 days is 72 hours. And every 12 hours, it decays in half. Right? So it decays in half every 12 hours. So how many times did it decay? How many times did it decay? For every 12 hours, it decays in half. After 72 hours, it decayed. So we have to divide 12 into 72. And I think we get 6 half-lives. Okay? It decayed in half 6 times. Okay. So what does that mean? 6 half-lives means it decayed in half, a half, 6 times, a half, a half, a half. That's 4, 5, 6. So usually we write that 1 over 2 to the 6th power. Well, 1 over 2 to the 6th, if you work it out, a half times 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 a half, I think it's 1 over 64. So only 1/64th of x remains. But we started with 512 grams. So if we do 512, right? Let me make sure I do carefully. 512 here. Okay. 512. And now we're going to divide by, what did I say? By 64. Right? And we get 8, just what I thought. So we have 8 grams of X of X. That means how much element Y, if it converts into Y? Well, we started with 512 grams, so there has to still be 512 grams on the table, but 8 grams are X. That means 504 grams are Y. Okay, 504 grams. All right, let's go on. The half-life of element X is 5 weeks. 5 weeks. Okay, let me do a different color. Okay. 20 weeks. After 20 weeks, how many times did it decay? Well, every 5 weeks it decays in half. In 20 weeks, 20 divided by 5, so it has 4 half-lives. All right, that means a half times a half times a half times a half. Or we'd say 1 over 2 to the 4th. And a half times a half times a half is 1/16. So there's only 1/16 of, what do we start with? 144, I guess that's micrograms, right? So if we divide 144 divided by 16, hopefully we get 9, I think. Yes, 9 micrograms of X. That's all that's remaining of X. So how much Y? Well, how much? 144 minus 9. So the amount of Y should be 135 micrograms of Y. Okay, because 135 plus 9 adds up to the original 144. Okay. Oh, these are all the same. They're not so bad, I hope. All right. The half-life of element X is 6 years, same problem. After 18 years, so how many times it decay? Well, every 6 years it decays. So if you go 6 into 18, we have 3 half-lives. Okay, 3 half-lives means it decayed in half, a half times a half times a half. Okay, so that's what? 1/8. 1/8 of the original was 112, right? So if we divide 112 divided by 8, we should have 14, I think. So we have 14 kilograms of X. And how much Y? Well, subtract 14 from that, and we get, I guess, 98 kilograms, I guess. Excuse me, of Y. You double check my math. Okay. Excuse me. All right, now I do the second type, the other type of problem I do. Okay, so in this problem, I tell you the half-life, and I want you to see how much is remaining. In these problems, okay, I'm telling you the half-life, and we want to know how much is produced. Okay. So the half-life of X, oh no, this is another one, sorry. The half-life of X is 9 hours. After 63 hours, so how many times it decay? Well, 63 into 9 means we had, I think, 7 half-lives. I'm sorry. These are the same type. Okay, that means we have a half. I'll do it, write it out, a half, 7 times, times a half, 3 times a half, 4 times a half, 5 times a half, 6 times a half. 7. So that's 1 over 2 to the 7th power. There was 7 half-lives. And I think that's 132, 64, 120, 1 over 256. So we have 1 over 256 of the original 512 times 512 milligrams. So that means there's 2 milligrams of X remaining, and therefore there's 510 milligrams, subtract 2 from there, of Y created. Okay? All right, now I'm doing the other type of problems, okay? So now um, we want to find the half-life. So here we want to find the half-life. So after 48 days, only 1/16. So 1/16 means it decayed in half 4 times. A half times a half times a half times a half. So we have 4 half-lives. I'm writing HL, half-lives in 48 hours. Well, 4 half-lives in 48 hours means 1 half-life, just divide by 4. 1 half-life equals 4 into 48 is what? 12 hours. Okay. So here we found the half-life. Next one, 1/32 remains. So 1/32 is a half. We have to do it 5 times, as you'll see, times a half, times a half, times a half, times a half. That's a fourth, an eighth, a 16th, a 32nd. So that's 5 half-lives in 40 days. So therefore, 1 half-life, just divide by 5, equals 8 days. See, these are pretty easy. All right, next one. Keep going. 1/64. Well, this is going to be 6 half-lives, but 1/64 is a half times 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 a half. That's a fourth, an eighth, a 16th, a 32nd, and 1/64, right? So we have 6 half-lives in 1,200 years. So 1 half-life, just divide by 6, should be, I guess, 200 years. Okay. Not so bad. Okay, next one, same thing, same thing. You should try to do these before I do them and pause this and do it. Okay, 1 over 128. Well, since 1 over 64 was 6 and 1 over 128 is going to be 7, but we'll do it. 1 half times a half times a half, 3, 4, 5, 6, 7. Half times a half is a fourth, an eighth, a 16th, a 32nd, a 64th, 1 over 128. So we have 7 half-lives in 112 hours. So now we divide by 7. So we have 112 divided by 7, and we get 16. So 1 half-life equals 16 hours. Okay, 7 half-lives in 112. So divide by 7, 112. Okay, and that's the answer. All right, one more of these. Okay, one more of these same types. Okay, so now we have 1/8. Oh, that's easy. Even I can do it. A half times a half times a half. So there's 3. That's equal to 1/8. So we have 3 half-lives in 340 years. So if we divide by 3, 1 half-life, 3 into 3, 340. Oh, I meant to put 240, but that's okay. I don't care. I should have put 240, but that's okay. And this is 113.3 years. I meant to put 240. 240 would have made it even 80 years, but that's okay. All right, that you know how to do that. All right, now we do the balancing. Again, we know we have to balance the top numbers and balance the bottom numbers. Once again, if you do the exam and you see you do the balance, say the top numbers, and only one answer in the multiple choice has that top number, then you don't have to do the bottom. That's the correct answer, and move on to the next question. All right, so let's see. We have 6 of these alphas. So 6 times 4 is 24. Right? Plus 0. Wow, I didn't put anything else. All right. So we have 24 on this side, and that's got to equal 8 times 0 is 0 plus. So this has to be 24. Okay. And then if we do the bottom, okay, I'm making this crap up. This is 12. And this is minus 3. So that's equal to 9. So 9 has to equal 8 plus blank. All right, so the blank has to be 1. Never heard of this, so this element doesn't exist, but that's okay. This is our answer. That's our answer. Doesn't matter if it doesn't make sense because these are just practice. Okay. All right, let's do the next one. Again, we'll start at the top. Doesn't matter what we start with. It doesn't matter. Okay, here we have 9 times 0 is 0, plus 4 times 4 is 16. So we have 16 plus blank has to equal 0. And this is 12 and 84. So 84 plus 12 is 96. This has to equal 96. Okay, if we subtract 16 from both sides, I think we get 80. If I did that right, I think the answer is 80. Okay, next we do the bottom. Okay, and we have over here 9 times negative 1 is negative 9. 4 times 2 is plus 8. 8 minus 9, we end up with minus 1 plus blank has to equal 7 plus 6 plus 41. So that's 1354. So this answer should be 55. 55 minus 1 is 54. So that's my answer for that one. Okay. Balance, more balance. Okay, keep going. Again, you should do this before I do it and make sure we agree, or you can correct me. Okay. All right. 8 times 0 is 0. 28 and 108. So 28 plus 108 is, I think, 136. And that has to equal 0. And that's 12 plus 12 plus blank, right? So 12 plus blank has to be 136. So if I subtract 12, I get 124. I think 124 plus 12 is 136. Okay. Next, we do the bottom. Okay, we have 8. We've got 14. And we've got 64. Okay, so 22 plus that is, looks like 86 if I did that right, right? 22 plus that 86. Okay, and that has to equal, this is negative 9 plus 6 plus blank. So this is negative 3 plus blank. So subtract 3 from something, we get 86. So this clearly is 89. Okay, so the number here is 89. These are so easy. Don't get these wrong. Just do your math right. All right, final one, and then you can go out and play. Okay, we'll do the top again first. It doesn't matter what we do first, so don't think I'm doing it every time on top. I'm just doing it. Here, that's 0. And here we have 40 plus something has to equal 0 and plus 16 plus, I guess that's 63, right? So this has to equal 79. Okay, so if we subtract 40 from 79, we get 39. So this should be 39, I think. 39 plus 40 is 79. Good. I think my math is getting better. And then finally on this side, we have 5 times negative 1 is negative 5. 10, that's plus 10 times 2 is 20, right? And then we have blank. So 20 minus 5 is equal to 15. So we end up with 15 plus whatever this blank is, has to equal 6 plus 8 plus 49, right? And that's 14 plus 49 is, I guess, 63, right? And if we take, now you could just subtract 15 both from both sides, right? So 63 minus 15. And what do we get? We should get 48, right? 48. And there's our answer. So again, I hope you know how to do these balancing. I hope the half-lives are not the worst things in the world, and that we're pretty much set. Okay, we're ready for exam 2. Okay, next stuff we'll be starting will be chemistry. All right, I guess that's it. Have a good day, and I will post this as soon as it is processed.